Hello and welcome to this GCSE Combined Physics exam preparation video on waves in air, fluids and solids. And don't forget to like and subscribe. Waves can be either transverse or longitudinal. A longitudinal wave is where the direction of disturbance is parallel to the direction that the energy is travelling. So we have our diagram here with the direction of the energy transfer and the direction of the disturbance. We also have areas of compression where the wave comes together and areas of rarefaction where the wave moves apart again. Examples of this kind of wave are sound waves and P waves, which are a type of wave generated by earthquakes. These waves need particles and so are mechanical waves. The particles themselves do not travel along the wave, they only oscillate, vibrate, around a fixed point. A transverse wave is where the direction of disturbance is perpendicular to the direction that the energy is travelling. So on our diagram we've got our direction of disturbance and you can see that that is perpendicular to the direction that the waves are moving in. Examples of transverse waves are ripples in water, all electromagnetic waves and S waves which are generated by earthquakes. Some transverse waves are mechanical waves and need particles, for example water ripples. The particles do not travel along the wave, they only oscillate around a fixed point. Some transverse waves are not mechanical and do not need particles, so can travel in a vacuum, for example, all electromagnetic waves. These are some of the key terms that you need to be able to describe a wave. Amplitude. This is the maximum displacement of a point on a wave from its undisturbed position. Wavelength. The distance from a point on one wave to the equivalent point on the adjacent wave. Its symbol is lambda and it's measured in metres. Frequency. The number of waves that pass a point each second. Its symbol is little f and it's measured in hertz. The period. This is the time taken for one wave to pass a point. This wave shows reduced wavelength and so it increases the frequency. The period of a wave is the time it takes for one complete wave to pass a point. The equation for this is t equals 1 over f, or period equals 1 over the frequency. The units, period, capital T, units are seconds, lowercase s, frequency, lowercase f, units are the hertz, capital Hz. The speed of a wave can be calculated using the following equation. V equals f lambda, or wave speed equals the frequency multiplied by the wavelength. The units are wave speed, little v, is in metres per second. Frequency, f, its units are the hertz. And wavelength, lambda, its units are metres. You can find the speed of sound in air and the speed of waves in water by following these simple procedures. First, sound is a wave and waves reflect. In the case of sound, we call this an echo. If you stand a known distance measured with a tape measure from a reflective surface, such as a wall, and measure the time taken between the sound being emitted and the echo being heard, and measure this using a stop clock, you can then halve the measured time and substitute the numbers into the equation distance equals speed times time. Rearrange and calculate the speed. For a water wave, you can time how long it takes for one wave to travel the full length of a trough. You measure this time using a stop clock. Measure the length of the trough using a metre ruler. Then again, use the equation distance equals speed times time. Substitute in your numbers and rearrange to work out the speed of your water wave. Both of these experiments are more accurate if they are repeated and means are calculated. Any anomalous readings should be ignored and left out of your mean calculations. And don't forget, you'll also need to revise the required practical for calculating speed in waves and in solids. And that's it for this video. Thank you so much for listening.